First, thank you very much for the invitation. Okay. In this talk, I want to talk about the lifting problem in the mainly the category of series algebras, in category of the seesaw dynamical system, and the category of the group wave dynamical system. But the first, I will start with the category of the seesaw algebras. Let A, B, and B, A and B be a seesaw algebra. R be a closed ideal of B, and the definition map P. And also, in the class, sometimes I use Q as the definition. P. And suppose that we have a linear map from A to B mod I that is a completely positive and interactive map. For positive, I mean that phi carries the positive elements of A to the positive element on the right side of this algebra. And we say completely positive if the induced map on the matrix algebra level also is positive for every matrix algebra. Okay, and then the lifting problem for phi is to determine whether or not you find a completely positive linear map psi or A to B that we have to completely find out. Okay, here first I want to say something about the theory. The importance of the existence of completely positive linear loops can be traced back to the Arison works in the extensions theory. Arison looked at the lifting problem positive answer when we have this the seesaw algebra be commutative, and on the right side we have the coordinate algebra on a separate basis. But the importance of the existence of the group in the extension theory is by x of c of x, I mean the equivalent classes of the extension of the c of x by compact operators. Okay, it was already known that it has a semigroup structure, but it was a question, the big question that if it is a group and then existence of the inverse boils down to the positive answer to the lifting problem. And then, okay, what we can say about arbitrary seesaw algebra, not necessarily unital seesaw algebra, exactly the same case is a C of H. It is a semigroup, but the existence of the inverse is related to the positive answer to the lifting problem that I mentioned in the first slide. And the join of efforts proved that if A is a separable seesaw algebra and the phi is a nuclear map, in particular if A or B are nuclear, then the phi is a nuclear map, then one always can find a lifting. And that it means that in particular the extension of A for separable nuclear seesaw algebras is a group. But now I want to know if you are interested in lifting problem in the category of the seesaw dynamical system. When a group presents, okay, I want to give assumptions that if G is a locally compact second quantum group, and I have a seesaw algebras with the action of the G on A and a B. I have an equivariant completely positive contractive linear map. And then, okay, I want to know this, the existence of the lift side, not only a completely positive and linear, but with some type of the equivariance property. But this is something what I should expect from this equivariance property. Indeed, in order to formulate these more precisely, I will first explain the motivation to study, to look at this problem. Indeed, with Hausdorff Bartella, we were looking at this problem, and then during solving this problem, we came up to the equivariance problem. So I will just explain these motivations, and then during this I will also explain that how I want to put some equivalence property themselves. Okay, for this I need to recall the definition of the zero examples. Let X be a locally compact Hausdorff space, and I be a C-SO algebra. I could say that A is a C0X if we have these non-degenerated star homomorphisms from the C of X to the center of the multiplier of the A. And the reasons that many people are interested in C0X algebras is that they are naturally fibered origins. This means that for every X belongs to X, I can associate C-star algebra that is called the fiber over that point. And then the definition is like this: that first we consider this ideal in A, and then AX is the quotient of A mod by X. And now every A can be viewed as a function. That this AX is in fiber AX. Then we have now this bundle of the C-star algebras. We can combine topology on this A to make it upper semi-continuous C-star bundle. But by upper semi-continuous means that the map from, for every A belongs to A, the map from X to R, understands every X to the norm of this AX is upper semi-continuous. And then interesting thing is that then A, the first A that we start, is just isomorphic with the space of the continuous section vanishing at infinity. And then is also one-to-one correspondence. If we start from an upper semi-continuous bundle, we can arrive at C0X algebras by this formula. Also, I will return back again when I'm talking about the case. Okay, but now I have A, C0X, I have the H fibers, AX, and each fiber is C-star algebra. So now it's interesting questions that if we have a property P for our C-star algebras, we know that each fiber of the AX, each fiber AX has this property. Under which conditions I can say that A has this property. And also another direction, but usually the other direction is easier. That if A has a specific property, it's easier to prove that each fiber has that property. But the converse is more difficult. Okay, but there are several works in this direction. Maybe the one of them that for me is interesting was the work of the Dowlot that in the winter. That if each fiber is strongly self-absorbing C-star algebra, then what we can say about this A. But I just remember, I just recall that these strongly self-absorbing C-star algebras are the one that they absorb. It means it's they're isomorphic with their tensor product, but in a strong way. And they are very important in the classifications of the C-star algebras in Elliott program. And then the Dowlot and the Winter proved that if we assume that X, this basis space X, has a finite dimensional, then if each fiber is isomorphic to the fixed strongly self-absorbing algebra like B, then A is isomorphic to Cx tensor D. But again, in the classifications program of CSO algebras, the C-star algebras are supposed, or you can expect that the C-star algebra is classifiable if it absorbs one strongly self-absorbing C-star algebra like Combs algebra or UHF algebra or Jiangsu algebra. And by absorbing it means that A is isomorphic with the A tensor with the dan strongly self-absorbing. After the Winter, Hirschberg or the Winter proved that if each fiber absorbs fixed strongly self-absorbing, then A also absorbs. If again the underlying the basis space X is finite, has a finite dimension. Now, this double generalized the strongly self-absorbing C-side algebras to the context of the C-star dynamical system. And also the Hausdorff that shows that it is a very useful notion, especially if in the dynamical systems absorbs in a strong way, absorbs as a strongly self-absorbing dynamical system. Then the studying of the structure. So with the overview, we investigated the equivariant versions of the Hirschberg integration in the way that A is a G6 algebras, and then we have some again induced actions on the each fiber. And then now we assume that if each fiber absorbs this strong self-absorbing action, what we can say about A. I said that the other direction is easy. This is the difficult one. But for this, we need a new characterization of absorptions of a strongly self-absorbing action by using the almost equivariant completely. And it is a theorem. But if you look at the okay, if you look at this part, you will see that we need to find this side that have this almost equivariant sense in this sense. That we fix finite set F here, finite set D, and finite set O is an equivalent to compact set of G, that we have this almost equivalent property for some G on a compact space, or finite set of the G, and B on the finite set. But indeed, if we do not have any action here, then this psi is coming from the Schoenfeld problem. And then, but here, since we have an action, we need to find some leaf with a specific almost equivalence problem. And this lets us to look at the lifting property in the category of the C-star dynamical system. And the first formulations of the lifting theorem in this category with in this theorem that G be a second countable locally compact group, and we have a 2G algebras is separated, P I D and better invariant ideal, then we have a quotient map in the position that bar is just the negative actions on the quotient. And then we have a completely positive productive linear map, which admits a completely positive linear distribution. Then, for every epsilon greater than 0 minus f of A, compact subset K of G, there exists a completely positive contractive linear map. That the first is the gift, is the leaf, and then second is that we have this equivariance property. But first, I do not assume that the P is equivariant. Okay, if it's equivariant, then we don't have a leaf there. But here, I want this equivariance behavior of the star depends on also the equivariance property of the field and the given axiom. Okay, before giving this proof, I want to explain more about this theorem. Okay, but still, since we are living in this, we have a separable algebras and the second countable one, we can always find that this here from A to B that are leaf, and that is then we just get rid of the get rid of the epsilon, and then we have the limit in this. Okay, now. Okay. But now, if A and B are unital and the phi is unital, the Schoenfeld theorem says that in this case we can find a unital lift. But in our case, when there exists and also G and we have a G algebras, then we don't always have this. And indeed, we need some condition. The condition is that if there exists just some unital completely positive maps with this property, then it is almost equivalent can be chosen in a Okay, but the first thing is that if G is amenable, then by the date, the induced action of the G on the stated space of the A has a fixed point, and then if we consider this fixed point state, it means omega, then it is a G equivariant, and then it's just take every row n to be omega, and then this condition is automatic. So in the case of the amenability, we don't have, we all guarantees that we always have a But the next slide, I want to explain that the case that everything is unital A, B, and C, but we cannot find the unital almost equivariant. Assume that the G is a non-nominal A is a nuclear CSI unital, and then what is the full and reduced cross product are the same. Okay, so we have several examples. If G is exact, I think it is we had amenable actions on some compact Hausdorff space, and then since these amenable actions, if A is C of X, then the full and the reduced are the same, and also we can take some exact group which is not amenable. Now we consider P of A from A direct from C to A, and then this P is identity. If we find a unital completely positive linear map which are asymptotically equivariant, then the point is that by this side, if we compose it here, then we arrive to some phi n. Sorry, this is a phi n, and then this phi n. We have a cluster point in the Wittgenstein topology, and because of the asymptotical equivariant, and there is this cluster point in the Wittgenstein topology is a equivariant property. So then by this cluster point and this property, we can show that the full group CS algebra and the reduced group CS algebra are the same, and that is a contradiction. So the impression is that existence of the unital leaf should be somehow related to amenability. But still, I needed to make the another formulations for lifting property in order to make this relation more precise. But I think that in these two slides, we have this impression that only amenability is somehow related to the existence of the unital lift in the some appropriate category. Okay, so now I wanted to return back to the proof of the theorem 1. Okay, but before going to the general case, I will consider two special cases. When G is a compact and when G is amenable. When G is a compact, we have a Hall measure. And then in the theorem, we assume that there exists a lift. And we have the Hall measure, so we just take the average of the lift by the Hall measure over the G. And then we can obtain the equivariant, almost equivariant lift. But in this case, the compact case, it is indeed equivariant. And the second one is an amenable case. In amenable case, we have a Fourier sequences. And then again, we have a lift, we have a Fourier sequences, and then we can have some averaging process, and then we can produce this almost equivalent lift from the ordinary just But what about the when the G is not necessarily compact and not necessarily amenable? We have still some averaging process, but at this time, this averaging process is somehow on the some approximate identity. So the first lemma is the variant result of the Hausdorff. Introduce to get some approximate. Let's use the locally compact again. Second one level, and then we have RD sigma uniform for M, and then for every separable CS algebra M0 of M, you can find an approximate identity that we have. It is almost commute with the element of mu, and the third is that is very nice property with respect to action. For all compact sets, this maximum goes to the zero. So the idea is that we want to somehow replace this approximate identity instead of the Fuller sequence or Hausdorff in the So, I just mentioned just that if I have the multiplier algebra, then I again have two actions, and I will use the notions during this class. Going details on the actions on the M of I and also on the Kaufman algebra, Qi, Mi, and then another action, use actions by Donald Bar. But then the point is that these two actions are not norm-continuous actions. They are just continuous with the strict topology. So I just take the continuous part of these actions. But before proving the main theorem in the general case, we just consider the expansion case. That the quotient is Q1. And the proof first is covered in the data special case. But the proof is that we have this. Since I is separable, then we can find M0, then we find this Xn from the Kasparov lemma, and then now we have this theta n, that is defined by Xn. And now this is this averaging process. Instead of the averaging over the Fuller sequence of the formation, they have this theta n k. But this one, by some old work of the Thompson and the Manilov, is the convergence in the strict topology of the MI. And mainly because of these, we need to consider first to look at the Hawking algebra and MI. And then now we can show that this each theta that is convergent topology with the leaf. And then now with the choice of the Xn, especially the third property that it shows that is almost fixed by the action. For the some leaf enough, we can find from this theta n to this almost equivalent. This is the idea here. So I think that the idea is mainly here that the averaging process is under this now. So now we return back to the main theorem. We know the results in the case of Hawking algebra, and we want to return back to have it for any arbitrary quotient. The idea is using the Buchweiler invariant. So I just first recall it. If we have any of the extension of these algebras, then we can have this Buchweiler invariance from this C algebra to Hawking algebra. And by this Buchweiler invariant, we can also translate our main theorem to the previous propositions. And then I can construct such map with this E, and this one is also, we have some Buchweiler invariance there. And then by help of this diagram and the Buchweiler invariant, we can find we can translate our lifting problem into the previous case, in the 14th case, and then solve it, and then by this case, we can return back to the our equation. So this is the idea. So now we did explain the first versions of versions of our lifting problem in the category of the dynamic system. But now, we come back to the question that I discussed before. Does the existence of almost equality according to the analysis? But for this, I need to reformulate again my equivalent property. I will just start with that if I have the surjective scalar homomorphisms between two algebra that during this talk G is always locally compact second number field, and asymptotically equivalent linear section is we have this asymptotical property that they are asymptotically linear, asymptotically contrastive. I will again return back to these slides and make everything really precisely, but I want to mention that here we have the lifts, a family of the lifts which are not linear. They are asymptotically linear. I will explain. I will make it more precise. So now instead, as you saw before, we have before we found some sequences of the almost equivalent. Here we really need to make it stronger and to have a big family over it. This is varies from 1 to infinity. And if we have this definition, and also we have this, then we can show that if G is annulable, then every compact matriciable G space X, the match proportional, admits an asymptotically equivalent linear section, which is asymptotically unital. And just I need matriciable to be sure that we are in the separable the separable system. Okay. So I see a very good idea that why I need to have this family that varies between 1 to infinity, and then how it is related to this asymptotical condition that I put. Again, I have these two projections, P1 and P2, and I can find these asymptotically equivalent intersections from C of X to C of XT for P1. And now I will consider these two system algebras CB1 infinity and C01 infinity. With the C1 infinity, I can construct this map from C of X to the PC algebra by the help of the asymptotic. And then by the quotient map, I can compose as and then I get some map but then but we look at this property of this map. Since P is asymptotically equivariant, and by the definitions of C0 and CB and the P, this map is equivariant. And since P is we have asymptotically linear, this one is linear. And also asymptotically contractive of the first leaf is needed. This map is contractive. So now just compose it some state here, we can introduce a G invariant linear contraction into C, which takes 1 to 1. And the reason one is that because the lift is asymptotically. And all of them means that we found the G invariant properly measures on X. That is equivalent with the amenability of the G. But for the converse, in order to show that the converse is true, I just need to introduce another lifting problem. So is that I'll prove that C implies A, but later I want to briefly explain that also A implies B if I add some other statement here. That also these statements are related to the another formulation of the equivariant. Okay, but also so I want to do this, and also I want to mention another thing also. If in the main theorem, the first theorem that I mentioned about the we assume that there exists a lift, and then we construct an equivalent lift. But there are examples that there exists no lift, and what we can say, and then the next formulation it also covers the lift. We do not assume that any lifts exist. So for this, again, I need to define that indeed if such lift does not exist in the theorem 1, then what we can find is that a continuous family of is definitely from A to B for the phi, that the phi was from A to B mod I, that these lifts, they are just lifts, even no conditions on the linearity, that are asymptotically linear, asymptotically completely positive, and asymptotically G phi equivariant in distance. So instead of the finding one almost equivalent lift, I found this continuous family of the lifts. But here everything behaves asymptotically close to the properties of the field. Phi is linear, but this lift is asymptotically linear. If phi is completely positive, this lift is asymptotically completely positive. And we have this asymptotically G equivalent one, that this one is very similar with the formulations of the theorem and the statement of the theorem. Okay. So just very briefly, what I mean by these notes. Then, okay, first I need some continuity conditions here, that there are continuous paths and also equicontinuous ones. And we call it uniform if each datative stands on 1. So by joint, each datative stands by joint, but asymptotically linear exactly this which you expect. And instead that we have this equality each datative, this is supposed to be and also we call asymptotically contractive, we will have this property. Asymptotically positive if the negative, because every positive, every separate elements have a positive and negative part. So it means it's in the limits we don't have a negative part. And also asymptotically completely positive, so we have this asymptotically positive in the matrix algebra level. And now for the list, I think that they are asymptotically G psi equivariant lift if it is asymptotically completely positive. Okay, now I want to make everything precise. So, the first theorem that we obtained here is that if G is second from the derivative from attributes, and A also and B beta are universal algebra, is G value ideal of G. And the A here separately considers algebra as meaning a G invariant space. And then we have the unital completely positive transaction linear map. Then we can find a unital asymptotically invariant for psi. So here there is, as you see, that there is no options for existing at least one leaf for psi. But on the other hand, here we need some G invariant space. Okay, maybe I will explain this right. The idea of the proof of the theorem is very similar to the idea of the proof of the first theorem. We first go to the integral level, and then we use the same average processing. We have the Hausdorff lemma. But the point is that if you remember, the averaging was just pi over n, but here also you need to take care of this t from 1 to infinity. And here, in order to make everything well defined, we need this invariant space to control, to define the theta t in the when t is much bigger. So in this is the example that we will use in the proof. And so the proof is just basically the same as the proof of the case, the theorem 1, but I can say that more complicated. In this is maybe somehow similar to the sum computation that was done in the ether by Hickson. But the idea is very similar to the theorem 1. And then the theorem 1 is not does not exist anymore in the preprint. If you look at in the archive, but still I found it more useful to talk about that one because it's easier to follow the proof. Then also it gives idea that's the proof is in there. If you can see the proof. Okay, and the second one is that if we go to the non-unital case, everything is easier, and then we do not conditions the G equivalent stay here. So we can always find such asymptotical equivalent for this. And now I can prove fully is the new characterizations of amenability of feature. We already see 1 and 2, and now I have 3 here. That means that for every expression, I have the unital asymptotical equivalent. This is also with the help of this, I can go from 3 to 1. So as far as we know that when we finish this work, we of the existence of the unital almost equivalently. So I can say that this is the new characterization. So what else I want to say is that so now I have a new characterizations of amenability for groups. And now it was very tempting to see that what we can say about the amenability of the group weights. If we can find the structure characterizations for the amenability of the group weight, but this is very difficult in the beginning. And it still is the second one is the ongoing work with and then okay, the first is that amenability of group weights are important, but the difficult part is that we have several notions of the amenability of the group weights. that we don't know whether they coincide each other or not. And we hope in this project that we can also find some some answer to the lifting problems in the category of the groupoid C-star algebras. And then we will see this if this in the unital case is related to the notations, some notations of amenability of groupoid or is completely independent. But now I just very briefly just mentions that how you can formulate the first lifting problem in the category of the groupoid dynamical systems. I'll not talk about the groupoids, but I think that she did not mention the definitions of the groupoid. But just very briefly, I want to say this, particularly that I want to the definitions. I have the set, some composable set with the two operations, the inverse and the product, and by this we can, since we have the composable, just compare it with the groups, that in the group case, every two elements are composable, but here we don't have this property. They are partially composable. And then we have the G0, that is the unit space. In the group, we have just one unit, but here we have more because all the actions are partially defined. And then we can define the two maps, the source map and the range map, like this. Then we can, and then the second case is that if the G is the group, just the G0 is the identity of the E. And the second one is that when the action of the G on X, then we can have a groupoid. So in somehow G, the action of the groupoid generalize both groups and the actions of the groups on X. Okay, that's very important. But now first I want to look at the category of the groupoid dynamics. So what is the definitions of the action, groupoid action on C-star? We have a locally compact Hausdorff groupoid. C0, G0 algebra. The G0 is the unit size of the groupoid. Then the action of the G is a family of a G. So here should be also G0. No, but this one is correct. Alpha G is the isomorphism. That each isomorphism from this ASG to ARG, all of them are C-star algebra, so it is isomorphism, between C-star algebra. Then we have this property like in this case, but since just for the G and H that are composable. This is the definitions of the action, but without any continuity condition. And if I want to put some continuity conditions, that this defines the continuity actions from G to the pullback of A by the range. And now, what we expect, and we are still working, and we expect to obtain is this result, that we have the locally compact second countable groupoid. I need a second countable groupoid here because we may need some type of the Hausdorff lemma, and this Hausdorff lemma maybe I can say that exists in several works of the Bohm, working on the Bohm-Kohn conjectures, but my supervisor and I were persuaded that we can obtain the really good Hausdorff lemma, like the one that we made also for the groupoid case, but we need to verify it. And then there are A and B are G algebras, I be a G invariant ideal of the G in the G sense. And then the process is, the first attempt is that we just look at that there exists a C0 is linearly. Then we can find any time F from C of the G, C0x linear map. That we just need to look at this almost equivalent property in this way. It means that they just look at the fibers, fiber-wise. but not only if, but also some continuity for over K. So maybe I just before finishing, I just explain a bit about here. First, we remember that in the theorem 1 also I assumed that there exists a leaf, and then Hausdorff theorem guarantees the existence of the lift when the A is the nuclear and the separable. But here also we have some results of the Hausdorff and boundaries that they define the C0x nuclear C0x algebras. That a C star algebra is called C0x nuclear if each fiber is nuclear, and also the field is not autosomally continuous. This C star bundle that we associate with the C0x algebras, but this is continuous. And then they showed that there exists a lift, the C0x lift for them. So at least here, these conditions satisfies when a C0x nuclear. So what we have is some. This is first we wanted to follow the same approach we have done in the group case. There are all of that because you look that we went first to MI, the multiplier algebra. But if A is a CX algebra, then M of A is not a C0x algebra. And the first difficulty appears here. So we really cannot follow the same approach like the group case. But still we have some ideas there. And the other is that, okay, in the group case, we really cannot do any modifications in the proof of the Joya approach or the Armstrong proof of the non-equivariant case. But here, the second possible approach is just to maybe just ask some idea from the Joya proof. And then, but then we have some problems of the continuity because we have the fibers and then we need to glue them. So this is just ongoing work. So we just group on the first this type of the liquid property in the category of the group dynamical system, and then look at the amenability of the group. For example, if G is the amenable group point in this topological sense or measure-wise sense, or that if, then we can guarantee the existence of the unifier here. This is the aim of the project in the loop. Okay.